Hi guys, and welcome to today's lecture. Today is March 29th. Let me pull my notes in here. And I can't read my history of missing energy. Yeah, okay. So we're doing the charging of the capacitor, and we found somehow that after a long time, and we recognized how long that time is, it's actually not that long, relatively speaking, compared to our scale. And it's of the order of RC. So when you are in an RC circuit, you have a resistor and you have a capacitor, you multiply the two numbers, and that gives you a time scale. If you wait an RC time, that means what? Basically 60% of the charge is already there. If you wait 2 RC, you're in the 90th percentiles. If you wait 3 RCs and more, actually you have practically fully charged. Then an RC could be of the order of a microsecond. So before you blink your eye or even look around, the capacitor is fully charged, at least on our scale. Sometimes the resistor there is made so big to tame the charging of the capacitor. And in this situation, it's actually advantageous to have tau to be less, more time for it to charge. So you would want that sometimes, and sometimes you want it the other way around. Especially in the discharge cycle, sometimes you would want the charge to build up over time. And especially during the turn on and turn off of the equipment, usually you have a capacitor in there, and you would want that to be discharged over a resistor when it's done and set. That's why there is that warning. Even though you have unplugged your device from the power plug, you have to be very careful when sticking your hand in it, because you could have capacitors that still have charges in them and did not fully discharge. So there is warning on almost all electronic devices because of that, because of the fact that you still have charges in the capacitor and you would want to get rid of them. In addition to capacitors, you will see later on another device called the inductor. That will be after the midterm. Okay. Inductors also store energy, but they don't store it in the form of charges. They store it actually in the form of currents. Okay. Here is the deal for this week. We know Wednesday is a holiday, and I really want you guys to enjoy your holiday and basically commemorate what it represents and everything, because I think it's very important. What I'm going to do for you, though, is I'm going to record a problem session that I'm going to conduct, do some problems. I'm going to already today do some problems with you. And actually, the charging of capacitor, honestly, is an example of how to use Kirchhoff's rules. And we're going to do problems, I think problem 19 and problem 29 from this chapter, but believe it or not, you'll have a lot of chapter practice before that. I'm hoping still before the spring break is in, because immediately after that we have a midterm week. I will have with you guys a chapter 27 introduced, namely the magnetic field. So we'll introduce chapter 27 before the spring break, albeit it's not going to be concerned with the midterm, but it's going to have implications on the second midterm, if you want to call it that way, and then also the final. So chapter 27 will be introduced before the spring break, because the week after spring break is really testing week, although I will record stuff for you guys, so you still have to do stuff during that week, those who are not testing, because we only have 1 day of tests and the other day is actually still, I will be on campus, but for you guys are not, you're only going to be testing on only 1 day, on a Monday or on a Wednesday, depending on the group you're in. And that is basically how the format is. Okay, so let me share with you the screen to see where we stopped last time. And please, if you don't understand something, do not leave it to the end, okay? Or do not leave it to ask for it later on or anything like that. Please do interject right away and let me know so that we can get that thing done, okay? Anyway, so share chapter 26. So let me remind you of how chapter 26 went so that we are all on the same page. Okay. So chapter 26, we had, let me go back all the way to the top. Okay, so what we have in this case, we have an EMF battery, basically. We have a resistor R. Sorry, here. We have an EMF, we have a resistor R, and we have a capacitor. Usually, like I said before, we turn the switch at a certain point. And that is when we look at the watch and say, okay, this is the time. We're going to call it t equal to 0. At that time, there was no charge in the capacitor. Our goal is to achieve a certain charge in the capacitor. Our goal is to build the charge in the capacitor. So we said, okay, we want to have Q charge in it. So we're going to allow it to charge. It turns out, after we work out the math, that it charges according to this expression. So this is the charging of the capacitor. So if you are asked to problems related to this expression, transition between not fully charged, because at t equal to 0, 1 minus 1 is 0, because the exponential of 0 is 1, so there was no charge. After you wait a long time, the exponential becomes 0, and the full charge becomes CE. So you indeed build charge in it, and how much charge is going to be CE. So this is the charge that you have actually added to the capacitor. And we immediately ask a question. Of course, the current in here is just the derivative of that stuff. So that's another expression that is of interest to us, is the current too. So we needed to understand of how the rate at which we're building charge is the current, okay? And in this case, we drew the graphs, and it is asymptotically approached the full charge, CE. And in this case, the current that is supplying this charge to the capacitor starts from a high value, which is epsilon over R, up down to 0. So basically, this is what's going on. And this is very critical for your problem solving sessions and exams and things like that. Initially, the current is just epsilon over R, as if there is nothing in here, as if there is absolutely no obstacle whatsoever in here. So during the first stage, when the switch immediately turned on, this is just like another wire. That's it. So when you're doing equivalent circuits and they tell you immediately after you replace, if the capacitor did not have any charge with them, you just replace them by straight wires, okay? Because at that point, the current is all of it here, and it's equal to epsilon over R. Then if you wait a very, very long time, the capacitor will be fully charged and will prevent any more current. So this becomes like an open circuit. So it's open after a long time, okay? And it's short-circuited immediately when t is just barely above 0, okay? So this is a very important thing that you really need to note when you're problem solving, because you can clearly see this expression here. At t equal to 0, the current is exponential of 0 is 1, so it's going to be epsilon over R, okay? So we have no problem. So this is as if there is nothing in the circuit other than the EMF in here and the resistor, because this one doesn't exist. It's just a wire, basically. When t goes to infinity, the current stops completely, because exponential of negative infinity is 0, so there will be no current. So you still have a battery, you still have a resistor, you still have a capacitor, but there is no current flowing for it. That means it's an open circuit at that point. So this is actually a technique to solve problems. You have to remember this one, because it's very important. And I think we're going to go through enough examples that you're going to be reminded of these points. Anyway, we addressed the question of energy, because it's very important, because once we place that much charge, which is CE, in the capacitor at the end, when we waited after a long time, we really have an amount of energy, which is just the charge divided by 2C. And the charge is CE, so you square that number, it's 1/2 of CE squared, CEMF squared. And then we asked, where is this energy coming from? The only suspect in here, the only culprit in here is the battery. Okay, that's the only one that supplies energy. That is exactly what you're paying for, as a matter of fact. You pay for that energy. So we calculated that energy by multiplying V of the battery, which is the EMF, times the current. And the EMF is constant. That's what the battery does. It has a constant EMF, times the integral of the current. The current is actually We found it to be, what is that value in here? Epsilon over r times this exponential. So all I have to do is integrate this exponential between 0 and infinity. The integral of the exponential is just another exponential. Don't forget you're going to drop negative 1 over rc times epsilon over r. So that's going to be negative c epsilon. And the value, the boundaries of integration from infinity and from 0 to infinity, and that's going to give me another negative 1 that cancels the sign and becomes positive, because it's very important. It has to be a positive energy, because this is the energy that we're draining from the battery. So this must be an energy that we're gaining somehow. So it turns out to be C epsilon squared. And the question then is, if we got C epsilon squared from the battery, half of which, 1/2 of C epsilon squared went to charge the capacitor. So where did the other half go? And obviously the culprit in here is the resistor. Okay, so it might have gone to heat the resistor in the form of heat inside the resistor. So let's calculate that heat now. So this is today's topic. Let's find out if indeed the difference is there. And if it's not complete, then we have to account for it. So let's find that energy. So inside the resistor, we know the rate, it's P, the power, times dt. And it's integrated from 0 to infinity also. And the power in the resistor, this formula is Ri squared, okay? Where I times R is V, again, it's VI, okay? Where I times R, Ohm's law, is V equal to Ri. So this is basically just a rewrite of that same expression. So it's still the same formula, except that this is the power now inside the resistor. So it's going to be Ri squared. So if I calculate this number, Ri squared, I squared is epsilon squared over R squared times the exponential from -2, because I'm squaring the exponential of T over RC. Again, I took just that expression and I squared it. What is it? The current inside the resistor. I squared this number. So it's going to be epsilon squared over R squared times the exponential of -2, because the exponential times the exponential is negative twice the exponent. So again, we're going to use that expression and we're in business. So we have the energy now that is dissipated. This is wasted, actually. Dissipated in the resistor is going to be given by, again, the integral of R times this number. Obviously, the R and the R cancel, so we'll be left only with one of them in the denominator. So it's going to be epsilon squared over R times the integral from 0 to infinity exponential of -2t over RC. So it doesn't look any different than the other one, actually, as a matter of fact, with the exception of this 2 in here in the numerator. So again, when we integrate this expression, we're going to bring the inverse of this term in here, which is going to be RC over 2 with a negative sign. So it's going to be negative RC over 2 times epsilon squared over R times the antiderivative, which is -2t over RC, evaluated between 0 and infinity. This R and this R cancel. And this number in here at infinity is equal to 0, and at 0 is equal to 1. So this is a -1, which cancels that negative sign, and is going to end up being exactly what the doctor ordered, in a sense that this is 1/2 or C epsilon squared over 2R. Oh, so there is no R in it anymore. Sorry. Okay. So this is how much energy was wasted. So let's tally things now. So from the battery, okay, we took C epsilon squared of energy. Here it is. This is how much we drained from the battery, C epsilon squared. Now we stored in the capacitor 1/2 of C epsilon squared. Here it is. It's just Q squared over 2 over C, 2C. And then when we did the algebra, it turns out to be 1/2 of C epsilon squared. So again, this is how much energy we actually have it in the capacitor. And we also wasted, not wasted, in R, this much, 1/2 of C epsilon squared. Here is the amount. So everything is accounted for now, fully accounted for in terms of the energy. Does this problem make sense to you guys? Or shall I say this concept?
Yeah, that makes sense.
Okay, very good. So we're going to take now the other route, and that is the discharge of the capacitor. It's going to be the problem in reverse, actually. If we're doing this in the lab, we will have actually the battery sitting just in between the resistor and the capacitor. And I'm sorry, because we need another resistor on the other side. I'm trying to think of a way. No, we have it in such a way, the switch in an AB switch, where you turn on for the charging and you turn it off and the discharge. And in this situation, the current will still go through the resistor. And now you don't have battery anymore because you don't want charge. You want to get rid of the charge. So let me draw this one conceptually. So this is what's going on now. We have a capacitor and a resistor. And that's it. We're going to take now the current I in this direction because we have a charge Q in here and we have a charge Q in here. The only thing you have to be careful with now is this current is not that of charging. It doesn't build charges, draining charges actually. I'm sorry, there usually is a switch somewhere in here because you don't want to start this one. You want to start it at t equal to 0. So there is a switch in here. So at S is turned on at t equal to 0, Q is actually equal to Q naught. If you wish, it's the old value from the previous charging stage. So it's equal to Q naught. And we expect at the infinity that time, when time as it moves along, that there will be no more charge. That we expect Q to be going to 0. That's how basically we expect it. And the other thing in here is that now the rate at which the charge is discharged from the capacitor is at this rate. So this is the rate of discharge. We're not building charges anymore. We're actually draining charges. So this is the rate of discharge. Okay. So it doesn't matter where we start since we don't have a battery now. My convention goes through the window. So we're going to take any point in here. So I'm going to start with this point, go through a voltage drop. This is actually negative drop, not a rise, but it's a negative Q over C. And now this is an actual drop of Ri. And then we come back to the same point because switch has no resistance or no change in potential. So in this case, the equation becomes simply equal to negative Q over C plus Ri equals to 0. So there is no EMF, no nothing in here. So this is Kirchhoff's rule for the loop because I took it this way. Okay. So there is a rise in potential in here, which is translated to a negative drop by Q over C, because I'm going from the negative side to the positive side. And there is an actual drop in potential in here, because I'm taking the current in this direction. I'm following the current, falling with it. So that is a drop in potential and coming back to the same starting point. So this is true. Now, the other thing in here is that I know the rate at which the current is being discharged is this much. So I need to find I to be positive in here to make sense. Otherwise, we have a problem. Okay. So if we write this expression now, it's going to be minus Q over C minus R dQ over dt equals to 0. Obviously, I'm going to move things around. So I'm going to move this to the other side. It's going to be a positive. So it's going to be R dQ over dt is equal to negative Q over C divided by R. And we have the same thing. Negative dt over RC. So this is the expression that we ended up with. All I have to do is integrate both sides. The integral of dx over x again. What is that?
ln x.
It's the natural log. Thank you very much. Have a nice day. So there's an ln here of q equals to Again, the integral of dx in here is just t over RC plus a constant. Always add a constant because we're just working with the indefinite, basically integral in this case. So exponentiate everything. So it's going to be q sub t now. And sure enough, it's decaying exponentially. Exponential of minus t over RC. Time is a plus a constant times the exponential of a constant, which is just another constant. So this is another constant, okay? Which is the exponential of that constant. So whatever that number end up to be is fine. So here is the deal. At t equal to 0, q of t equal to 0 was equal to q naught. So from here, we can say that that constant times exponential of 0, which is 1, that means the constant is actually q naught, the initial charge in the capacitor. So q sub t then, in general, is going to be the initial charge in the capacitor times exponential of minus t over RC. Obviously, this is similar, except now we're discharging, because if I wait t equal to infinity, the exponential becomes 0, and that's true that I have lost charge. So at t goes to infinity, q approaches 0. So this is basically how this looks like. Initially, the capacitor has a charge q naught, and then is going to decay exponentially. The characteristic of the decay again is tau, which is RC. How big is RC? Depends on your applications. If it is too small of the order of a microsecond, before you blink, it's gone. If it is for industrial or probably some other applications, you might end up with a high value. And here again, that is basically where you want it. It's going to be probably a millisecond or maybe a fraction of a second, hundredths of a second or something like that. It's still, most of the time, it's a long time. Do not count on it. If there is a warning on your device telling you do not touch the device because it might have charges in it, believe it. And there are other devices that hold energy too that could cause a lot of damage. So you don't want that, okay? So you don't want to be in a situation where you're going to be actually the part completing the circuit and actually yourself becomes part of it, and that's not good, going to be good. How about the current? Remember the current, I said it's equal to negative dq over dt because this is discharge now. So it's going to be negative, the derivative of this, guys. Negative times negative is going to be positive. It's very important, as I was saying in here, because we took it in that position. That means it's really discharge, not anything else. So it's going to be a q naught over RC times the exponential of minus t over RC. Again, this is the current. So we'll start from some current at which we're discharging this one in here. So this is the current, which is q naught over RC. RC is of time, okay? The units for RC are in seconds. It's very important, okay? Because the units for R are what? Volt divided by current, which is ampere. Remember, V equal to RI. So the units of R is the units of volts divided by ampere. And the units for Q is actually ampere. So where is the volt in here? The capacitor, I'm sorry, the capacitor, not whatever, not the charge. Okay, the capacitor, again, you have Q over C is equal to a voltage, the volt for the capacitor. So that means the units of C are the same thing as the units of a charge divided by a volt. So when you have that in here, when you multiply these two numbers, so this is volt over an ampere times a charge, and a charge is going to be an ampere times second divided by volt. So the volt cancel and the ampere cancel and everything cancels, so that this is actually a time. So when we call it a time characteristic, we really mean by it a time, really. It's really in seconds, okay? So that is actually a time. So this scale in here is in T. And you can scale in here, this is 2/3 of the way after tau. And it's almost 90% after 2 tau. And after 3 tau, it practically is 0% left, okay, of charge. So you can use that as your scale, basically, for the circuit. Same thing for the current. The current also decays exponentially, as you can clearly see, and it goes from finite value all the way back to 0 to, in the same time characteristic tau2 equal to RT, okay? So this explains things. In terms of the energy, you ask, okay, I have a charge in here, which was Q naught when I started the circuit, and when I lose the charge, I lost energy. So where did that energy go? It must have gone to the heating the resistor again. So the initial energy in this case, initial depends on how much charge you have, which is Q naught squared over 2C. And then after you wait a long time, it's going to be this energy dissipated in this resistor. So you can do the calculation, you're going to find it exactly. All you have to do is just basically integrate the expression Ri squared from 0 to infinity, and you have Ri squared, you have I squared, which is what? Q naught squared over RC squared, R squared C squared. And then you have to integrate this one with it twice. So it's going to be the integral from 0 to infinity R times Q naught squared over R squared C squared exponential of minus 2t over RC. And again, you're going to pull negative, in this case, from this expression, dt. And you will have, first of all, the R cancels the R. And there will be another R in the numerator coming from this expression that cancels the other R. And there will be a C that is coming in the numerator that cancels one of the C's. So you're going to be left with negative Q squared over 2C. And the integral of the exponential is just another exponential of negative 2t over RC evaluated between 0 and infinity. And this is 0 minus 1. And the minus takes care of that. So all of the energy that was in the capacitor, in this case, is dissipated in the form of heat in the resistor. Okay? Are we clear on these two problems? Make sense?
Yeah.
Okay, very good. So let me check first of all the lecture to make sure I did not miss any important points. Do not rely on my lectures, honestly, guys. Make sure, and I know I have a lot of questions at the end of each chapter. So you guys know that some questions are not covered. So you better be actually ready to go through the book and go through it. And it's important to go through that. I didn't talk about the electrical measurements, but basically the ohmmeter and the voltmeter, it uses actually a principle that is still not there yet. It uses magnetic induction, and that's still way back chapter 28, actually. So technically we really cannot. So we talked about Kirchhoff's rules, and they are very important. And that's it. That's chapter 26, done for you, okay? Check on it, very good. So now I'm gonna tackle two problems, and they're problem 19 and problem 29 from this book, okay? So we're doing problem session now. Not only we're done with that, but we're doing actually problem session. So the first problem I'm going to do with you guys, I don't want to write with this thing in here. It's too small anyway. This is problem 19. Problem 29. I'm hoping to at least do these two today. And let's look at problem 32. Problem 47.
Are these the numbers that are going to be in the 14th edition or the 15th edition?
This is the 15th edition. If you guys don't have access to the 15th edition, it should be just the e-text from the website, from Pearson Learning. Just go to the e-text, you'll find them. All of this I'm talking about, they're actually from the 15th edition. They're on pages 871. And right now I'm looking at 873. And let me see. I think I still have way more than this. Okay, this is just a starter thing, okay? We still have way more than that, okay? We still have, this is what, 4 problems? You're looking at least to 4 more problems for a total of at least 8 problems, potentially 10 problems that we need to discuss, okay? Looks problem 84 is a fun one, actually. If you look at it, it's actually trying to find the equivalent resistor between a structure that is completely messed up, okay? So that's what you can do with this kind of things. Problem 81 is an NPN transistor. Oh man, I don't know if we do that too, honestly. And again, we still have way more. So this is just an appetizer for from this chapter. Okay. So let's look at problem 19. Problem 19, who is in the 4C class in here? Anybody? Physics 4C? I know at least one is here. Not necessarily with me, with anybody. Physics 4C? Did anyone take Physics 4C? Any? Okay, at least one person did not. How about the others? Are you taking it, or did you take it already? Or planning to? Okay, planning to. Okay. Okay. Okay, I know at least one of you guys is sitting from this class, who is present right now, is sitting in my Physics 4C. So this problem 19 actually deals with the stuff that we learned from Physics 4C. That's to be more specific, chapter 17, okay? If you did not, you must have heard of it in your chemistry class, so don't worry. So if you have had chemistry and you heard about calorimetry, basically the measurement of the specific heat, okay, then you know, okay? If not, then it's not really hard to understand. Here is the deal. Let me first of all draw the circuit because it looks awful, but it's not really that, looks intimidating, but that's look only. It's not real thing in there, okay? So let me share again screen. So these are the problems that I'm looking at so far, 19, 29, 32, and 47, okay. Problem 19, that's page 871, by the way, okay? So where should I start drawing? Okay, it doesn't matter. So we have a junction in here, and we have 3 resistors. And they are in parallel. Okay, I'm sorry. What am I talking about? They're actually not themselves. They have actually in series with the other 2 resistors. So this one is actually has in series with another one. This one is series with another one. And this one is in series with another one. Now we can say that this 2 series 1 are in with the 2 series 1 and this 2 series 1, the whole thing is actually in parallel. Okay, so this is problem 19, by the way, if you're wanting to pay attention with this thing in here. Now, the first 4 resistors are 10 ohms. So this is a 10 ohm, 10 ohm, 10 ohm, and 10 ohm. And these 2 resistors are 5 ohms. Okay, when I'm doing problems, guys, this is the time when you go and before that, okay, you need to have a piece of paper and a pencil or a pen, and you're doing these things, okay? This is not a spectator sport. This is not where you're going to be holding your phone and checking and paying attention. No, that's not how it's going to work. Or you're probably watching TV or doing something else. This is the only way for this one for you guys to work is to go and grab a piece of paper. So if you don't have it right now, you need to do it right now, okay? Go and grab something and draw the same things and follow with me the calculations and write every single thing, doing it yourself. That is the only way for you to really practice these things and have it sync with you. Otherwise, it's gonna basically, you're gonna skip on it entirely, and that is not good. So now this whole 3 are connected now in series with another resistor of 5 ohm. So this is a 5 ohm. And then we have a battery. Which way the battery points? So this is the cathode. This is the anode. This is the positive side, basically. This is the negative side. And we have an EMF of 30 volts. Okay. And in here, we have another resistor And this resistor is a 20 ohm, first of all. And in here, they tell you it's in a container, styrofoam, and that styrofoam has water in it. So we have water in here, okay? So this resistor is basically trying to heat water for you. We're trying to raise its temperature using that as a, like, for example, cooking coffee, preparing your coffee or something like that. And then after that, you have, technically, you really have to have a switch somewhere, but that's fine. So this is how the circuit looks like. So we have water there, okay? So in the circuit, a 20 ohm resistor is inside 100 grams of water. So the mass in here of the water is 100 grams, okay? Of pure water that is surrounded by insulating styrofoam. Because if it's not pure water, if it's, for example, water with salt in it, that means that it's a conductor. So we don't want that. We want it just an insulator so that we warm it up, okay? If the water initially is at 10 degrees Celsius, so the TI for the water is 10 degrees Celsius. The T final for the water, you want it to warm it to at least 58 degrees Celsius. So the T final is 58 degrees Celsius, okay? So that's basically the condition. The question is, how long will it take for its temperature to reach this one? So the question is the time T. Here is the deal. If I find the current that is flowing through this resistor I, then I can find the power, P, which is equal to Ri squared. If I know the power, and I want to have this, I want to know how much heat is absorbed by this water. Heat that is absorbed by the water depends on the difference in temperature, and the heat is given by this expression mc delta T. So this is from chapter 17, or physics 4C, or chemistry. If not, if you have never heard of it, this is basically what it is. So each material, in order to raise its temperature by an amount, you have to supply its heat, basically. And that heat depends on the amount of water. If you're going to heat up a bathtub of water, it takes more heat than if you're going to heat up your cup of coffee. So that's basically essentially what that mass is coming from. And each material has its own specific heat. Some materials need a lot of heat to raise their temperature a little, and water is one of them. And some other materials, you don't need that much heat. Like, for example, iron takes very little thing to get it to warm up. So this is what the specific heat is. It's a characteristic of the material. So once we have that, the heat is actually energy. And this heat, now we need time for it at this rate of P. So all of the energy that is dissipated in the resistor in here, in this 20 ohm resistor, so R in here is 20, and I is this current. Once we find I, we're in business, basically. And once we find what the power is, then we're going to plug it in here to find that the heat, which is equal to power times time. And this will give me an equation for time, which is just given to Q over P. So I can find Q. Q is just the mass of 100 grams times the specific heat of water, which is, by the way, 4,190 joules per kilogram. So I need to convert this one to a kilogram to use this expression. Per degree Celsius, or per Kelvin, okay? Kelvin and degree Celsius are the same because we're dealing with a difference in temperature in this case, okay? And we're going from 10 to 58, so this is going to be 58 minus 10, which is going to be 48 degrees, or 48 Kelvin, okay? So we have the heat. We can find it from this side. Mass of the water is given. Specific heat of the water is known. And the delta T, in this case, the change in temperature, we want desirably to go from 10 degrees Celsius to warm it to 58 degrees Celsius, okay? So that's basically the whole objective in here. And that is the resistor in here. So we have all of these things. Does this problem make sense to you guys, how we're going to tackle it?
Yeah, it makes sense. But just as a reminder, what's the C for the Q equals MC?
Okay, Q equals to mt delta T. The mass that you want to raise its temperature. C is the specific heat. And delta T is the change in temperature.
Awesome. Thank you.
Q is the heat, which is an energy, okay? As long as there is no phase transformation and water stays water between 10 and 58 degrees. If, for example, you want to raise the water temperature to 117 degrees, then you have to account for the heat of, the evaporation there in this case. So you need the latent heat for water to include it part of the phase transformation. So you need an additional amount of heat to go from liquid to gas, okay? So if you're staying in the same phase, if you're staying in the same format, basically, which is water, then this is true, okay? Otherwise, you need to add the phase transformation in this case. Good. Okay, so this stuff you learn it in depth, actually, in physics. Honestly, physics 4C does not really, it deals with more other things than this one. To share with you the screen or the other screen? I don't know what I shared. Are you guys looking at this thing?
Yeah, we can see it.
The problem? Okay. So we can find Q first from the get-go. Q, the heat that is needed, is going to be the mass, which is 0.1 kilogram times 4,190 joules. So this is kilogram, joules per kilogram per, in this case, it doesn't matter which unit you use, either degrees Celsius or Kelvin, okay? Because the difference in temperature is going to be the same thing. So I'm going to use degrees Celsius, so it's going to be 58 minus 10. So let's find how many joules that is. That is degrees Celsius. Obviously, degrees Celsius cancel and the kilogram cancel the kilogram, and the energy is going to be in joules. So let me pull my calculator. And the calculator tells me 0.1 times 4,190 times 48, basically. Okay, it's 20 kilojoules, basically. 20,112 joules, okay? So that's what the calculator is saying. Obviously, I have too many sig figs in here, more than what the problem actually is dealing with. It needs just 3 sig figs. It's 20.1 kilojoules. 0.1 kilojoules, okay? Because you need to restrict yourself to the sig fig. So we have the answer for that. Now we need to find I. For me to find I really have to go through different things in here to find it. There is one easy way of finding it, and that is finding the resistance equivalent. So if we look at it from the vantage points of the battery, here is how the battery looks like. The battery looks just like an R equivalent, that's all. There is that I going through it, and it's the same I that comes from the positive and goes through, first of all, the 20 ohm, splits itself between these 3 branches, and each branch has 2 resistors. So now the split is combined in here and comes back as the same current through the 5 ohm. So we need to find the R equivalent. For that, we're going to work with the innermost. So this is how I'm going to tackle this problem. This ones, I'm going to combine them together. These are in series, so R equivalent for them is 20 ohms, just the sum of the R's, okay? Because they're in series. These are also in series, so the equivalent for them is 20 ohms. These are in series, so the equivalent in here is actually 10 ohms. So what I ended up with, and in this case, I have 20 and a 20 and a 10, all of them, they're in parallel now. So the R equivalent now between this 4, this branch in here, this entire section, as if I'm going to replace it by an equivalent, R equivalent for just this section, okay, not the whole thing, is equal to 1 over 20 plus 1 over 20 plus 1 over 10. Okay, 1 over 20 plus 1 over 10 to 20, that's actually 2 over 20, which is 1 over 10, plus 1 over 10, which is 1 over 5. So this whole thing is just like a 5 ohm resistor, because this is like 1 over 5 ohm. When I invert it again, and this is where a lot of people go wrong, they forgot to invert this R equivalent because they are actually in parallel. So this whole thing is just equivalent to a 5 ohm. So what this resistor is looking at, it's looking at a 20, followed by an equivalent resistor of 5 ohms, followed by an actual 5 ohms. So you have a 5 plus 5, that's 10 plus 20. That is actually, they're all in series now. So it's looking at 20 plus an equivalent of the others, which is 5, plus an actual 5 for a total of 30 ohms. So the current now that needs to be satisfied is simply V, which is, how much is V? 30 volt. And this is 30 ohms. So 30 volts must be equal to I times 30 ohms. Obviously, the I in this case is exactly 1 amp. 30 divided by 30 is, cannot get it any simpler than this. I mean, this is the simplest algebra that you can deal with. Okay? Now, we have the current. Now we're going to come back to this expression to find the power now. So the power in that resistor is going to be Ri squared. So the power dissipated in the 20 ohm resistor is Ri squared. And R is 20 ohms. And I squared is 1 amp squared. And this is going to be what? 20 watts. Okay, so this is the power. Now we have the power. We have Q, which is 20,112, divided by 20 ohms, and that should give me the answer. So the time T is going to be the total energy divided by P, and the total energy in this case is 20,100.
Wait, wasn't the resistance 30, not 20?
Was it 30? No, it's 20.
No.
There is no 30. I'm looking at the problem. Problem 19. 20 ohms. Jason, or whoever asked her.
I was thinking the equivalent resistance, but now I understand that it was just for the
Yeah.
resistor in the
No,
water.
no, no, yeah, you're right. That's a good question. It's a very good question. Where should I do the calculation? It's in here. The water is sitting just on the 20 ohms, not on the entire equivalent. Not the whole thing is bathing inside a tank in here of water. Just this one. That is the one that is used to heat stuff. Okay. This 20 ohms, only where the water is. So we found the current. We used the equivalent just to find the overall current, which turned out to be 1 amp. And that is the same current flowing through this one. Now, if you put it in here in this 10 ohms, it's going to be a different story altogether. You need to find this current actually in here. Once you find that one, that is the one you square and you multiply by 10. So depending on you put your tank in here, or container, the styrofoam in here. Okay. Since they put it in here specifically, so this is the one that is of interest to us. So now we have that. So it's 20,000 joules, basically, divided by 20 watts. And the answer should be, let me put my calculator quickly in here. That's this number, so 7 in it divided by 20. It's 1,006, basically. I know sig fix is only 3, so I'm going to keep that 1,006 because seconds. Because the unit of time is in seconds. So how many minutes is that? So if I divide it by 60 and then take the difference. So first of all, this number divided by 60 is 16 minutes. What is the difference between 1,006 and 60 times 16? In 46 seconds, I mean 17. 17 minutes, basically. You're gonna heat that water from 10 degrees Celsius to 58 degrees Celsius. Does this problem make sense to you guys? Very good. You really guys need to pay attention to these little details because they are critical. And a question that Jason asked is actually a very good question that you really have to pay attention to which resistance to use where. just because we found the R equivalent. What is the purpose of finding the R equivalent? The whole thing with it, just to find the total current, that's all. Because it turns out the total current is running through this one. Again, if the question was for this 10 ohm or this 10 ohm or that 10 ohm, I really need to find the current in there. Okay, since they made it life a little easy for us and they asked us for a 20 ohms, then I will use this one. If they put it around the 5 ohms, then we will use a different one. In that case, we will use a 5. What is that for? We use the 5 times the same overall current, which is in 1 amp. So that's going to dissipate a lot weaker energy. In that case, it's going to be 5 watts. Okay. So it's going to take more time to use this one to heat stuff than the 20 ohms. Okay. Because when you divide 20,000 by, it's going to be 4 times as much. It's going to take almost an hour. And then this is the concept that is outside of the scope of this class, which is this thing, Q equal to MC delta T. So once you know this expression, you have found you know the energy, and you're in business. Grant you guys that this chapter 26 comes after chapter 17, so the book has no problem with it. It's actually with the sequence of the classes that are offered in here in our college, in a sense that they move them a little bit different. So the chapter 17 comes actually after, for some of you, after chapter 26. And although I don't think that physics 4B is not a prerequisite or even a co-requisite for 4C. You could have taken them together with absolutely no problem whatsoever. It's 4A that is a prerequisite for both of them. Okay. So the other problem I promised to tackle is problem 29. Let's do problem 29. Problem 29 has 2 batteries, so you have to really be careful in here, because depending on which one is winning. And one of them is actually not known. We don't even know what its voltage across it is. We don't even know what its EMF is. So we have 2 batteries we have to worry about. So in problem 29, let me draw the shape. So this is problem 29 on the next page. I hope again that you're not watching me do things. You're actually doing them yourselves. Okay. So again, I have this resistor. Can you get rid of this line in here? It doesn't make any sense. This resistor of how much? 75 ohms. And then a junction here. And then I have a resistor of 20 ohms. Followed by a battery pointing this way. That we don't know its EMF. So this is a 20 ohm. Now we have a 30 ohm in here. Resistor. And in this junction, we have a battery pointing actually the same direction as the previous one, but we know the EMF of this guy, it's 25 volts, I'm sorry. And then we have a switch that is open. So this switch is open, not closed, okay? And then we have an ammeter followed by a resistor now. And that resistor is 50 ohms. So this is a 50 ohm. And finally, we have a voltmeter. Voltmeter, they always have to be in parallel, and ammeter, they always have to be in series. I'm sorry. Voltmeter, not an ammeter. Okay. So this is how the circuit look like. So the circuit shown in the figure, the batteries have negligible internal resistance, and the meters are both idealized. Okay, that means they don't have internal resistance for the ammeter, and for the voltmeter it has an infinite resistance. Okay, so there is no current flowing through the voltmeter. and there is no voltage drop across the ammeter. That is what idealized means in here. So the difference in potential between this point and this point is 0. So 0 volt across this one. And the current flowing through this voltmeter, I is 0. That's what idealized means. That this voltmeter has an infinite resistance and the ammeter has a 0 resistance. They are opposite to one another, okay? And the EMFs also do not have any internal resistance. That's what it means to be idealized. Find the EMF E with the switch open. So they have the switch open now. It's not closed. So there is no current flowing through this section. From this point to this point, there is no current, okay? So it's completely open, okay? The voltmeter reads 15 volt. So this guy, when S open, so this is the switch or S, the voltmeter across the 50 ohms reads 15 volts, okay? That's how much voltage there is. Find the EMF of the battery. Find this epsilon in here. What is that supposed to be? Obviously, this is the one that is pushing current because this one is disconnected, okay? When this one is open. So this one is pushing current, and the current in here somehow splits itself. And then part of it that's going to go through the 30 ohms. And because now there is no way for the current to go through an open circuit, so it has to continue its way and fall through the 50 ohm. And that is where this guy is registering 15 volt, okay? And then it's going to come back in here to the battery. This one that goes to the 75 ohm, they combine again into this one. So I have this node, and I have this loop, and I have the other loop. That's it. This one doesn't exist in the circuit when S is open. Okay. So what's the question again? Find E. So let's find this difference in potential between A and B. If we find that, we're in business. One way to find it is the following. Since we know what the voltage across the 50 resistor is, and this must be the current times the voltage, times the resistance. So this must be 50 ohms times the current. So this gives me a value for I that is flowing through this circuit, that is the ammeter is actually registering, is 15 over 50 over 50. And if I multiply this by 2 and multiply this by 2, it's going to be 30 over 100 or 0.3 amps. So there is a 0.3 amp that is actually registered in here going through this resistor. And the 0.3 amp must be also going through the 30 ohms too. So the same voltage now going through this one plus this one, the same current, because they're in series. In this case, because there is no way for the current to go through this resistor. That's why their current in here is the same current of 0.3 amp everywhere in here, at least this section. So this current is 0.3 amp going through the entire circuit and coming in here. We don't know what this value is yet. Okay, we'll find it, okay? So the voltage drop between A and B, VAB, is simply, which is VA minus VB, by the way, is simply equal to this voltage drop plus this voltage drop, and this voltage drop is 0.3 times 30, which is 9, plus 0.3 times 50, which is 15. So it's 9 plus 15, which is 24 volts. So it's going to be 0.3 times 30 plus 0.3 times 15 is equal to 24 volts. So the voltage drop between this point all the way to this point, back into this point, because there is nothing else up to this point in here, is 24 volt. And this 24 volt, I could compute it also this way too. It's this resistor, because I'm dropping actually in this current this way too, times this current, which I don't know what its value is. So I'm going to call this one I prime. So I know what this one is. It's 0.3 amp. But I need this I prime to give me also 24 volts on the other side, which is the same voltage drop. So this voltage drop also is 75 ohms times the current that is flowing through it. Since that is 24 volts, so the I prime then must be equal to 24 over 75, and this needs a calculator. 24 over 75 is 0.32 amps. Come on. If this thing crashes, please do not leave. Okay, we're not done yet with the lecture. Okay, so we're not done with class. So it's 0.32 amps. That's the current that is flowing here. And 0.3 amp is in here. So for the conservation of charge in here, there must be a current flowing from this point, which is 0.62 amps, because this one is 0.32 amp, and the other one is 0.3 amp. So the sum of these two is 0.262 amp. Okay. This voltage drop is actually across these points too, across the 20 ohms, which is actually dropping. But in here, I have to be very careful. Let's call this point in here ABC. Let's call this one C. Okay. And let's write this expression carefully now. So this very same VAB, which is 24 volt, by the way, which is VA minus VB, is actually VA minus VC plus VC minus VB. Okay. This is the voltage drop across the resistor. Okay. Because VA is a higher voltage than VB by 24 volts, actually. That's how the difference is. So that's how much we found. So in this case, this is actually equal to the current, which is 0.62 times 20. So this voltage drop is simply 0.62 amps times 20 ohms, plus this voltage drop. Now I have to be careful with this voltage drop. This is not actually a voltage drop. This is a voltage rise. Okay. This point here is higher than this point. So if I'm looking at the voltage drop between C and D, it's actually minus epsilon because it's rising potential, not drop. This is very important. So this is actually not minus because VB is sitting at a higher point. I'm sorry, VB is sitting at a lower point than VC. So if I'm counting the voltage drop between C and B is actually a rise by negative epsilon. So this value in here is negative epsilon. Okay, this must be equal to 24 volt. What is 20 times 0.62? Times 20. 12.4 volts. So there is a 12.4 volts in here. And I have actually another, in this case in here, a negative epsilon drop, because it's a rise actually in potential in this direction. Since we're going this direction, this way, we're going in this direction, in the drop, okay? So in this case, it's going to give me, what, 24 plus 12.4 is going to be 36 something, 36.4. So the EMF must be 36.4 volts. And now we have the value for the EMF, okay? So this answers the question about the voltage in here. Now, if you look at it from each way, each different way, in here, for example, in this loop, I'm going to look at it this way. I'm sorry, that's negative everywhere. That's not good. Let's go clockwise, okay? Following the current. So if I start counting, it doesn't matter. Let's start from the point B and come back to the point B. So we're going to fall in here by, actually rise in here by 36.4 volt. Plus in here the drop of 20 times, which was 12.4 volt. And in this case is actually another drop of 24 volt. Now this must be equal to 0 because we go from here and come back and we're going to end up back to the same point. If you do the algebra, you'll find that this is indeed 0. If you do it from the other side, it's still also 0 too, because you're going to be rising by 36.4 volt, meaning you're dropping by negative 36.4. And actually dropping now by 12.4. And in here, we calculated it to be 24 volt too. So plus 24, so that too is 0. Does this make sense to you guys? At least the how we arrived to this value of epsilon. If it does not make sense to you guys, you really have to have a pen. You're writing these things and going through it again. And if it still doesn't make sense, please let me know so that we go through this thing again. Good. Okay, very good. So the item in here is to verify all of my algebra today, okay? To calculate, to go through them, make sure it makes sense to you, okay? And all you have to do is just basically do the algebra, or show the actual algebra that you did it, because you really I want you guys to be masters of these things in here. So the part A, we answered it. So the EMF is 36.4 volts, okay? what will be the ammeter read when the switch is closed? So now we're going to come back to the same circuit and actually close the circuit. Close the switch, I'm sorry. So in the second part,
we don't see your screen.
I'm sorry. Thank you. So now we're going to come to this point in here and actually close the switch. And we want to find the reading in here at the current. Remember, initially we found the current to be 0.3 amps. That was flowing through this section completely. So that was the reading on the ammeter to begin with. But the current now will have a different reading. Why? Because you also have another battery in here. Okay. So we need to find basically the voltage across these points in here. And this is easy to do actually, because the voltage now across these points in here, they're not the same points A and B. The point B is the same, but this is another point. Let's call it D, for example. Okay. The voltage drop between D and B is actually 24 volt if I go in this direction. But if I go in the opposite direction, it's a voltage rise actually. So if I'm going from D to B, VD minus VB, VD minus VB, this is an actual drop, okay? On one side, it's 25 volt through the battery. That is an actual drop because I'm going from the positive to the negative. On the other side, this is an ideal. It has zero resistance. So it has zero drop in it. So the only drop in here is through the 50 ohms. So the 50 ohms will have 50 ohms times the current that is flowing through it, I, through the 50 ohms. Obviously, if I solve this equation, 25 divided by 50, the current now is, what is it? 0.5 amp, half an amp. Okay, so it went up. So this is the current going through the 50 ohms, and that's what the meter is going to register now. So initially it was reading 0.3 amp because you only have one battery pushing a lot of current through one section in here and the other section, and that EMF turned out to be 36.4 volts, which is bigger than this 25 volt. But now, helped by this 25 volt, the current now has increased because this is pushing in the same direction too. Albeit this one is stronger, so now it doesn't need to push as much in here. Probably the current will change in here, but that's another story, okay? So the current changes. That's the key thing in here. The current depends on the source in here. The source has changed already. And it's not only 36.4 volt. You have two batteries. And the two batteries are not working in the same fashion. They are not just add the two. If I put this battery next to this battery in here, yes, you can say, okay, the voltage now overall is as if it has a big battery. Basically, you take two batteries and I don't have two in here, okay? Take the battery and put another battery in here, another battery, and all of a sudden you have a bunch of batteries. Instead of 1.5 volt, you're gonna have as many in there, okay? And in some other configuration, you put them one next to the other. But if you look at the inner circuitry, this side, the negative of this side is connected to the positive, and the negative is connected to the positive. So you end up with an effective, far more greater EMF than what you have in there. But I didn't do that in this case. Actually, we have resistors between them. There is this resistor, there is this resistor, there is all kinds of configurations. So that's not that situation. So we did not just basically fuse the batteries from end to end. We just basically connected them in this fashion. Okay, I hope these two problems make sense to you guys and you go through them because they are the basis and the foundation for what needs to come next. Problem 32, I don't want to start it now because honestly, I needed to have it fully developed. So let's leave the rest for I'm gonna do at least two more for you guys. I know you have your vacation, your break, your spring break, which what you guys have still. I'm not spring break, the holiday break. But I'm gonna do at least two more problems. Were you guys going to go and actually do the actual problems too, and verify my calculations and finish it because I probably will not finish it, and that's gonna be part of the discussion too, and then. Do more problems with you guys when it comes on Monday, and then start chapter 27 on Monday, okay? I think the lab is still on for this week. I know we don't have class on Wednesday, so I'm going to leave the instruction in there. It's doing its time, and I'm going to give you the video instructions for it. And also, if you have difficulty with that, please let me know. Next week, we're going to resume things according to schedule. We hope to introduce chapter 27 by then, and then we will be ready for our exam. Okay? Good.
Sounds
Okay,
good.
very good. Okay, very good. So I'm going to stop the recording right now. And I will see you a week from today. So enjoy your holiday and see you a week from today, and watch for communications and stuff that is going to be posted on Canvas, okay?
Sounds good. See you next week, Professor.
Bye.
Professor.
Bye.